Hi everyone, my name is Judit Pérez-Romero. I'm a fourth-year PhD student in the IFT Instituto de Física Teórica in Madrid, and I would like to thank the organizers for giving me the opportunity to talk about this project of the sensitivity of the Cherenkov Telescope Array to dark matter-induced emission from the Perseus galaxy cluster. First of all, I would like to briefly introduce the dark matter paradigm. We have a lot of observational evidence of a matter-dark component of the universe amounting up to the 70% of all the mass of the universe. And we have a very wide range of different kind of candidates with a lot of different kind of masses, like for example, like the weakly interacting massive particles, the WIMPs. For this talk, I'm going to focus on the paradigm of the weakly interacting massive particles. We know from the standard lambda CDM cosmological model is the one giving the structure formation processes. In this sense, what we expect about this dark matter is that it forms around these objects some kind of halos, and that the candidates that we propose are forming these halos around the structures, the astrophysical structures that we see. From this, we expect that these candidates, the weakly interacting massive particles, can interact within themselves, annihilating or even decaying into standard model particles. And from these standard model particles, we are able to detect them in our telescopes. From this talk between the different kind of golden channels that are usually used for these indirect dark matter searches, we are going to focus into the gamma rays. Okay, so we want to find gamma rays from dark matter. Now we need to check where we need to look for. A golden target for indirect dark matter searches will be a target which is highly dark matter dominated, because the expected gamma ray flux is dependent with the square of the dark matter density profile in the case of annihilation, and linearly in the case that we assume the decay of the WIMP. Then we also want massive and nearby objects, because this flux is also dependent on the mass of the object and 1 over the distance squared with the distance. And it will be very nice to not have any other kind of gamma ray source in this kind of object. So no low or having a very low astrophysical background. So having this in mind, we look up to the sky and find different kind of targets. We have, for example, the galactic center, which is highly dark matter dominated. It's very massive and it's close. The problem is that we have a bunch of different gamma ray sources. We also have, for example, the asteroidal satellites, which are a bit farther and not so massive. But then the good point about the asteroidal galaxies is that we do not expect other kind of gamma ray emission from this object. And then other kind of targets that we can also consider are galaxy clusters. Galaxy clusters are the largest gravitationally bound structures from in the universe by gravitational collapse. They have masses of the order 10 to the 14, 10 to the 15 solar masses. These masses can be accounted in the form of baryons, which are distributed in galaxies and intra-cluster medium, but then up to the 80% of the mass of a cluster is in form of dark matter. Then we have the most massive objects in the universe and very highly dominated. Then these are the perfect candidates, the perfect targets to search for decaying dark matter, right? Because in the case of decay, the dependence is mostly with the mass. And then for the case of annihilation, it has been shown in previous studies, like this one that I cite here, that they can give comparative results compared to other prime targets, like for example, the asteroidal galaxies, as long as we assume the substructure that we expect from them. I will enter into details later about this substructure. The only problem about galaxy clusters is that we also expect other kind of gamma ray emissions that do not come from dark matter. Like for example, the diffuse emission that we expect from the hadronic cosmic ray part. Still, not clear detection has been made from this expected diffuse gamma ray from this hadronic cosmic ray, but some hints has been claimed. Right now, we know that we want to focus for our dark matter searches into galaxy clusters, but we need a telescope for that. In this sense, we are going to focus and we are going to work with the Cherenkov Telescope Array. The Cherenkov Telescope Array is the future of imaging atmospheric Cherenkov telescope for very high energetic gamma rays. We have two arrays. The first one in the north, which is will be located in La Palma, where we already have one of the telescope, an LST. And then it will be also the second array situated in the southern hemisphere in Paraná, Chile. About the consortium, we are more than 1,000 members in more than 200 institutes. More about the Cherenkov Telescope Array, it has a very good energy range, compatible and very complementary with respect to the energy ranges of other gamma ray experiments, like I'm going to show you right now. And we have three different kinds of telescopes. The smallest one with the SST covering the highest energy range to the LST covering the lowest energy range. So with respect of the comparison of the performance capabilities of CTA with the rest of the gamma ray experiments that we have this plot about the sensitivity, energy sensitivity here of CTA, where we can see that the highest sensitivity of CTA will be among 1 TeV and 10 TeV, so perfect energy range to target for weakly interacting massive particles in the case of dark matter, right? And then what we can see is that we can improve, CTA will be able to improve up to 1 order of magnitude the sensitivity that current IACTs have. So we have CTA, we have galaxy clusters, but we need a cluster to point our telescope at. In this sense, some years ago, when the White Science paper of CTA came out, some people arranged and made the effort to try to figure out which of the local clusters was the best to target for a gamma ray detection. And I want to clarify this because in this case, we were not aiming only for a dark matter gamma ray related detection, but to any gamma ray detection, to detect also these gamma rays from this hadronic cosmic ray part. In this sense, Perseus was determined and selected as the best galaxy clusters to point at, because Perseus is among the local clusters, the brightest in the X-ray sky, and it has optimal conditions for observation from the northern array. So some properties about the Perseus galaxy cluster: it's a cool, core, relaxed cluster, and it hosts two AGNs, NGC 1275, which is aligned with the X-ray center, and IC 310. Here I show you some previous work of this Science with CTA book. And what we are going to do right now is to go into a deeper analysis of the performance that CTA will be able to do about the gamma rays emission that we expect from Perseus. But first, I'm going to show you the dark matter modeling that we are going to do with Perseus. We want to compute the dark matter induced gamma ray emission from the Perseus galaxy cluster. And we are going to factorize this calculation into two factors. The first one is including all the information about the spectrum of the emission, which in our case is given by the WIMP spectra, by these results shown in this paper of Tirelli et al. From 2012, including electroweak corrections. And then we have also the astrophysical factor, which includes all the information about the morphology of the expected emission. And for this, we are going to consider two scenarios. The annihilation scenario, in which we are going to consider that two WIMP particles are able to annihilate themselves into gamma rays, and then the decay case, in which we consider that one WIMP is going to decay into gamma rays. We can see that the dependence is mainly of these J and D factors, that is what we call the astrophysical and factor in each different scenario, is they are only dependent in the dark matter density profile, in the case of the J factor for annihilation to the square, and linearly in the case of the decay. Then what we want to do is to perform a state-of-the-art parametrization of the dark matter in Perseus. And for this, we are going to include the dark matter distribution of the main halo of Perseus, but also according to the lambda CDM structure formation processes, we expect a bottom-up hierarchical scenario that the first structures that are formed are the smallest one, and then via accretional collapse, these structures form bigger and bigger structures. So then in these biggest structures, we expect a lot of these smallest structures, and we are going to include them, of course. So the way we are including them is to split our modeling of the whole Perseus galaxy cluster into the smooth part, what we call the main halo part, and then to average on the substructures part. because CTA is not able to resolve individually these subhalos or substructures. For the case of the main halo, we are going to use a Navarro-Frank and White profile. This falls in the group of Caspi-like profile, which most of the material is focused on the center, and it has been shown that it's pretty compatible up to the scales of galaxy clusters for describing the dark matter in these objects. And then for the case of substructure, we are going to follow a description for the population of the substructures that we expect from Perseus. And the description is depending on 3 different parameters. The first one will be the position they occupy in the main halo of Perseus. Second one, the distribution of the mass that these objects have compared to the mass of the cluster, and also the concentration that these objects have, because it has already been shown from embodied lambda CDM cosmological simulation that we expect from these substructures to be more concentrated than main halos of the same masses. So having this in mind, we want to bracket all the uncertainties regarding this modeling of the substructures that we expect in Perseus by establishing 3 different benchmark models. So in the case, we have the first case, which will be the minimal model, where we do not consider any kind of substructure. Then we have the MED model, which will be the best guess of how much these substructures can contribute to this astrophysical factor and thus yielding higher dark matter fluxes. And then the MAX model, which is an adequate upper bound of how much these substructures can contribute, right? Then applying all these to the measurements that we have from the Perseus galaxy clusters, we obtained 3 different J factors for the min, med, and max model, and 1 for the decay, because as we have seen, these smaller substructures do not have a proper contribution in the case of the decay because of their mass and to the distance. And what we can clearly see from these different values of the J factors is that having into account these substructures can enhance up to 2 orders of magnitude nearly the J factor that we obtain from an object, so having a really important role. Also, from this modeling, we have obtained this information about the spatial morphology of the expected emission in gamma rays, which is shown in these templates using the code clumpy that I show here. And what we can see is that the role of these substructures becomes more important in the outskirts of the galactic cluster, which makes sense and is completely compatible with using an NFW profile for the central part and for the main halo. Okay, so now we have the modeling part settled. So now we have the telescope, we have target, we have the modeling. So let's jump to the analysis. So okay, how we are planning to do that? Because as you said, we have different kind of gamma ray sources in Perseus. We have our dark matter models, okay, but then we also have the cosmic ray induced gamma ray that in our case will be used as background. And then we have the 2 AGNs that are in Perseus, in the 1275 in the center, and IC310 that in our case will be used also as a background. Then we are going to combine all this theoretical information with the latest instrument response function that we have from CTA and simulate an observation, and then test if we find a dark matter signal. And in the case that we do not find a dark matter signal, we put the standard constraints in the WIMP dark matter fetch space. In the case of annihilation, with the cross-section with the mass, annihilation cross-section with the mass, and in the case of the decay, with the lifetime of the dark matter particle with the mass. So for this, we have settled 2 different kind of pipelines for the analysis. The first analysis configuration, which is centered on the typical on-off analysis. And I said typical because it's the most historically used in the ISCT community. For our case, it will only include the gamma ray emission for the Perseus dark matter part and also the instrumental background. And we have 2 different approaches. For one, we will assume Perseus only as a point-like source, okay? the simplest and lowest level of complexity will give us the more constraining result. And then we have a second approach when we will use these templates that I just showed you for the on-off analysis. After different kind of trials, we decided to go with this kind of setup and having 300 hours of observation on Perseus. The good thing about this kind of configuration is that it will give us using the lowest level of complexity will give us the most constraining result, and it will allow to perform direct comparison with the latest results of the observation of Perseus that we have, that are the ones coming from MAGIC. And this is what I'm going to show you now. I show you the limits for the Perseus galaxy clusters, for the meta-annihilation model, and for the decay standard model that we have for on-off configuration, comparing the both kind of scenarios that I've told you for this on-off configuration. The point-like morphology, which is represented with the solid line, and with the dark matter template, which is shown in the dashed dot line. And what we can see is that in the case of the extended dark matter template, our limits are not so constraining as in the point-like case. That is what we expected, but for less than a factor of 2. In the case of annihilation, we can see that we are still a bit far from the thermal relay cross-section. But in the case of decay, we can see that compared with the latest results in the literature that are the ones coming from the observation of MAGIC, CTA will be able to improve the results of MAGIC up to 1 order of magnitude. Then we have the CTA configuration, the second configuration that we have, that is the template fitting. Using the magnificent field of view that CTA will have, we want to target for a more realistic physical analysis, which will be the template fitting, in which we will include all the different gamma resources that we expect in Perseus, that are the dark matter, the cosmic ray, the AGNs, and the background. So it will also allow to see correlation between components, and it will be our state-of-the-art analysis pylon because this more realistic scenario. Finally, I'm going to show the last part of this talk, which is the comparison of the 3 different configuration analysis that we have for Perseus. And what we can see is that in the case of template fitting, that is the most realistic one, which is shown as a solid line here, we get still a bit far away from the thermal relay cross-section, but it's the first time that we show this kind of result for the Perseus galaxy cluster. And compared to the point-like source, we only get a factor 2 to 3 less constraining results than for this simplistic case. So this is all. Thank you very much for your attention, and I will be very happy to answer all your questions in the rest of the session that we have. Thank you very much.